Welcome to the Regents Motion in a Plane problem set numbers 1, 2, and 7. We'll do the solutions here for those. Let's start with number 1. A batter hits a pop-up straight over home plate at an initial velocity, that's VI, of 20 meters per second. The ball is caught by the catcher at the same height that it was hit. At what velocity does the ball land in the catcher's mitt? Neglect air resistance. So with a quick little sketch, we start out with a ball hit upward with initial velocity VI, and we know that that is 20 meters per second. That ball goes straight up, and then straight back down, and is caught at the same spot from which it was hit. We know that at the top, the velocity here is 0 meters per second. So the question becomes, what is this final velocity at catch? Well, you may remember from our one-dimensional kinematics unit at the beginning of the year that the reason that the ball goes from 20 meters per second of initial velocity to 0 meters per second at the top is because acceleration due to gravity acts on it and slows it down. Well, that same acceleration due to gravity is what speeds it up on the way back down. Acceleration due to gravity is constant. So that's the key to the question, is that the acceleration due to gravity is constant. That means it's going to act the same on the way down as it does on the way up. If that's true, if it starts out at 0 at the top, what will be its final velocity at the bottom? And of course, the answer would be, it would return back to 20 meters per second. So that's the final answer to number 1. Number 2, in baseball, a fastball takes about half a second to reach the plate. Assuming that a pitch is thrown horizontally, compare the distance the ball falls in the first quarter second with the distance the ball falls in the second quarter second. First of all, the fact that the pitch is thrown horizontally is a bad assumption, but that's what they want us to do for this particular question. So we'll start off with the ball thrown horizontally with initial velocity. And let's suppose that it gets caught over here at that location right there. Okay? So compare the distance the ball falls. So they want us to take into consideration the vertical motion or the vertical height the ball drops. Well, what we know is that the ball, while it's moving sideways, is going to accelerate down due to gravity at 9.81 meters per second squared. What we know about an accelerating object is it gets faster and faster. That means it's going to cover more distance as time goes on. So if this represents the position of the ball after a quarter second, that means it would only have fallen this distance here. And then in the second quarter second, it will have fallen this distance here. Clearly, the ball is falling further in the second quarter second than it is in the first quarter second, and that's because, of course, it's accelerating downward due to gravity. So the answer is that it falls further in the second quarter second. All right, and lastly, number 7, you swing one yo-yo around your head in a horizontal circle, then you swing another one with twice the mass, but you don't change the length of the string or the period of revolution. How do the tensions in the strings differ? Okay, really neat problem here. Okay, so we set this up. Let's start off with, are either yo-yos accelerating? And the answer is yes, because they're both traveling in a circle So we put the C as a subscript on our acceleration, reminding us that it's centripetally accelerating. What's neat about this question is you also get to identify the force keeping the yo-yo in a circle. And as this problem describes, it is the tension in the string that keeps the yo-yo traveling in a circle. So we have a T equals an M, and then a V squared over R is our way to calculate the centripetal acceleration. Okay? All right, let's see what changes they made here. So in the first yo-yo, you swing it around your head in a horizontal circle. Then you swing another one with twice the mass. There's the difference between the two. But you don't change the length of the string or the period of revolution. Okay? You don't change the length of the string or the period of the revolution. What this, of course, does means that if you don't change the length of the string, that means the radius of the circular path remains constant. And if you don't change the period of revolution, that means the velocity remains constant. Side note over here for future reference, how would you calculate the velocity given the term period of revolution? Well, V is D over T. The distance would be the circumference of the circular path. So that would be 2 pi r, the circumference of the circular path, divided by how much time it takes to get once around in the circle. Well, that's called period. So you can see, by not changing the period, that the velocity remains constant also, because you're also not changing the length of the string. So the radius remains constant. Well, what they did do, though, is they doubled the mass of the yo-yo in the second part, in the second experimental trial there. And so what that would do, you can see a direct relationship between the tension and the mass. And so that means the tension also doubles. Okay? So there's your answer there. All right, more problems to come in class. And this is a nice set of introductory questions on both projectile motion and centripetal motion for our motion in the plane unit.